somewhat of a review, but from the perspective of kind of what are we actually dealing with. So chance events are any type of event that can have multiple outcomes, right? So anything that we can sample, that we can take an actual physical measurement of, can work out to be a type of chance event if the outcome is uncertain. So the uncertainty of outcome is a key factor in the processing of modeling. So if we flip this little coin here, we have what would be theoretically a fair coin toss, right? Should be a 50-50 chance. But if I simply do it once, then I will say that all of the examples, all of the samples that I have taken indicate tails, right? The single sample isn't going to really be able to tell us much about the underlying process governing the likelihood of future events. So any single sample is only as informative as whatever class or group it belongs to. In a simple binomial distribution, it only provides us with the parameterization of the outcome. Now, if I flip this 100 times, we start to notice something that starts to relatively concur with our understanding or our assessment of the 50-50 flip. But why are these two things not the same? Why does the practical aspect of the coin flip not match the theoretical? Should be a fair coin, right? Why do we think it doesn't match?
Tails wins more.
Tails wins more? Okay. If I just keep pressing this button, right, will it eventually get there? Should it? Yeah, it should eventually get there, right? That's based upon concept that most of you probably learned 3 and 4, central limit theorem. The idea that if we continue to collect any system of probabilistic distributions to a sufficient density, then we will ultimately converge towards the ideal or the theoretical system. But what happens is that convergence happens when? At infinity. So the convergence happens at infinity. Why is it that I've done this, like, I can just keep clicking this, and it's still never going to be perfect, right? It's never going to, and it's never even going to really be totally even close to where the underlying system is. Mostly because of the fact that this is computer generated, okay? I can see some arguments, and I'll give you some arguments later on. There's a guy who's a excellent statistician. He does a website called 3 Blue 1 Brown, if you've ever seen his stuff. He explains some of the underlying factors that affect this. But a good chunk of this is related to the idea that these systems of probability are based upon sort of incomplete models, and that the randomness is fed in through a seeding process. We put a number into an algorithm, and that outputs some aspect of the randomness in this particular case. With a simple binomial distribution, it's actually a lot harder to be able to get something that truly maps the underlying system. Now, talk again here about random events, okay? And we'll look at this website several times. I can put a link for you up on this website as well. This website's great because the fact that it makes many of the things we're going to discuss at basic concept levels. It shows you sort of what they do, what they are, and kind of how to work with that. So within this space, on the right-hand side, we have a universe. This universe is the sampling space for some random event. So if I start off by just sampling the distribution, I'm going to imagine that there are a bunch of people that live in this space, in this universe. And upon each moment, at each individual instance, I'm going to recognize a single individual from there. I'm going to sample or pull one person out. And this is two-dimensional space, right? So there's a two-dimensional universe, flat universe. So all these little flat entities are living in a flat universe. So meaning that the only really significant feature that each of these individuals have for us to be able to differentiate them with is what? What features do they have? Position. For position, all right? And how many dimensions is that? It's
Two.
It's a two-dimensional feature, okay? So each individual in this particular space is going to be getting a X and Y coordinate to be able to tell us relevant of their particular position. Now, at the moment, we haven't implemented anything to be able to differentiate them. We don't, they're all just living in the universe. That's how we're sampling this. We're gonna reset this real quick, and then we're gonna go about something. I'm gonna create a couple of little fictional nations in our little fictional universe here, right? And this little fictional nation up here we'll call Nation 1. Okay? It's gonna be blue, and I'm gonna draw another little nation over here to the right-hand side, and then we'll call that one 2, and then we'll have one little final group down here at the bottom, and we'll have a small region that doesn't necessarily overlap between those. Okay. Now, if I come down here and I click this sample distribution button, let's think about what is going to happen. I just want you guys to think about it for a second. If I'm going to be getting a plot, what is this plot going to be relevant to? What do we think it is? Look at the limits of the plot and tell me what you think that plot is going to output.
The area of each section?
That is true, partially, all right? The reason why I say that it is true partially is because the fact that area really is the only quantification we have relevant to the factor that we're actually sort of looking at. You could say that probability is in fact a area metric. Okay, I'm gonna go ahead and start the sample distribution. And what's gonna happen is if an individual is sampled, right, and their value of X and Y happens to fall within a space that's assigned to one of these little nations, then we will call them a member, a national of that space. Now, what we notice here is that universe, right, is still quantified. That's group 0. That's the area that's outside of our national space. Those are the tribal people that live outside of the known universe. This is ancient times, whenever the whole world wasn't already established as nations. So we have people that don't live in the cities, people that live in each of the relevant cities. Now, one of the reasons why I said earlier that the spatial aspects of this are in fact what's being represented by this is that you could conflate these two things. Think about it this way: if I take and sort of just drop randomly on top of that surface a single dot, let's say the wind's blowing around and it's a little grain of sand, and it can sort of go in any which direction and drop anywhere on that universe surface, right? That's the concept of randomness in the sampling base. Then the likelihood of it dropping on any given one of these 4 classes of space, the 3 nations we're interested in, and our 0 space, the remainder, right? The probability or likelihood of that grain of sand to drop on that space is going to be proportional to the amount of space allocated to that region. Essentially, that's what we're looking at. When we say probability, we say the higher probability is going to be allocated to the region that has the most space. Now, which one of these is highest?
0.
Because of the fact that there is more space that is unallocated than there is space that is allocated. We also notice that I drew nation 2 just ever so slightly bigger than nations 1 and 3, right? Nation 1's probably the biggest, or excuse me, so nation 2, nation 1, nation 3 in order of size. Now, if I keep leaving this running, what will this converge to? Exactly the spatial distribution, all right? I say it will converge to the spatial distribution. You say that it is spatial distribution, and I agree to that to a certain extent. But during the sampling process, the ratio of likelihood will be summational to what? 1.0, the entirety of the area space. So if I add up all of these guys across here, I should end up with the full summation of the spatial output. Now, is this going to be exactly right in this case? No, because of the fact we haven't sampled every physical area as a result of the random sampling that's occurring in this space. Now, this is actually a classification example in some effects. Partially because of the fact that we have a model, right? Our model is where I drew the boundaries for the colors. That's my model, that's what I thought it should be, right? When I see a little black dot hit the surface, and you notice the little black dots change the color of the region whenever they hit that region, okay? That means the system is classifying them as being a member of that region. Now, in a supervised environment, we would have examples. Those examples would drive our distinctions based upon where we put the borders of our little nations, right? So if we didn't have a map and we didn't have an understanding of how this space is supposed to be put together, what we might do is we might start off with our original sampling space, right? Where we have nothing going on there. Reset this. And what I might do is as these elements are hitting the surface, I would record where a sample of a specific city member hit, right? Then I would aggregate those together and I'm gonna end up with these little clouds, right? Little blue cloud, little yellow cloud, little pink cloud down at the bottom. You have to kind of imagine this because this particular simulation doesn't do exactly this thing. But the idea behind this is extracting information from samples or sampling a space are sort of two sides of the same coin. They're looking at the problem from both directions. Now, if I want to try to determine whether or not the borders I put into place are good ones, then I would have to evaluate my borders with another known set. That's what we're going to do. It's one of the things we're going to work on and we're going to talk about is how do we build the models, right? Both from attempting to imagine a new space, right? So let's say that I actually had one single group here in the center. And I had established that group to be my primary interest. This is the item that I want to classify, and I'll say that this one is sort of one versus the rest. None of the others really matter. It's just this one. I'm going to sample the distribution, and what's going to happen is as the samples are coming in, this is just going to give me a proportional ratio of space. Okay? All I'm going to be getting from this is you're either in or you're out. This is a binary classifier. When I think about it in terms of evaluation, how might I evaluate this? Well, since I can tell, let's say that some of these dots that happen to fall inside of this space here were actually labeled as white dots. Right? This is my model. This is what I expect it should be. But let's imagine that some of the ones that are being classified as blue, or being classified as true, are actually misclassified. They're incorrectly placed into the grouping. That would be an error type. Okay? That's making a mistake. So we're going to talk about this. This is, like I said, this is the visual example to sort of anchor some of the concepts. But we're going to go on to the Chapter 2 material. I will post this for you guys if you want to play with it. It is a cool little tool. And like I said, I will probably continue to use it right along because I can't really make visual examples that are quite that good, right? I've always sort of thought about it from the perspective of saying that if you really want to get into teaching, you should probably like take a graphic design course, and like a game programming course, and like a simulation class, because it is really necessary because media is such a core part of how we're learning to think. Right? So, and this is a primary example right here. Media is a big part of how we think. Advertisement is one of the things that's given as an example in the first part of this book. Matter of fact, it's about the first half of this book, focuses on this problem. All right? Now, I know this sounds silly to take half a book to focus on a problem, and also it sounds silly to consider things like radio advertisement and newspaper advertisement. When's the last time somebody saw a newspaper? You know? Like, they're dead. Newspapers are long dead. Okay, so what do we do here? What do we do here? If we want to make this relevant to us, we have to reformat it in our our head. So how do we reformat this? We have TV advertisement. What is TV? YouTube, okay? That's YouTube advertisement, all right? Let's bring this into the modern era. YouTube, radio, podcasts, okay? That's it's cool.
Podcast.
And then newspaper, this is, okay? You know, X, whatever. I don't know. I'm behind times. Exchanges, visions, I don't know what they are. But it seems like there's some kind of marketing opportunity there. They didn't fully integrate. It's just to pick a letter, it seems a little arbitrary. But we have the idea of distributing information over sort of a closed curated system. And the idea of it gaining revenue based upon exposure, right? So I have a media generation station, okay? Whether it be a television broadcast or YouTube channel, whether it be a radio station or a podcast, whether it be a newspaper or my Facebook, okay? Whatever I am that is taking content and putting it out to the user is making profit based upon what? Exposure. Okay, so how does that work? Well, that's based on the same sampling theory characteristic that we were looking at beforehand. It's the idea that my broadcast from any one of these given sources is actually going to be received by or hit within the correct demographic, the correct space of the market that is available. So the city is broken up into regions of, radio stations that are broadcasting to that area, or a county is broken up that way, or television stations broken up that way. My targeting of where I decide to advertise as a business is going to be a lot about trying to hit the market that I'm most interested in. I want to maximize my return on investment by advertising to those people who are going to be most likely to buy my product. So there is a relationship here, there exists a relationship here in 3 dimensions that each individual dimension has a relationship with the numerical number of ads being distributed on the platform and the relevant amount of sales that are observed as a result of those number of ads being put onto the broadcast source, right? What does this mean to us? How do we look at this and say something useful? Well, I want to try to say that the more ads I put out, the better I'm going to do, right? Put more ads always is going to increase your sales. There's actually a relationship in some platforms that doesn't have a strong correlational aspect, right? This newspaper, in this particular case, you can look at it. If you would say, the more advertisement, the more sales, how would that look relative to a line? What's the rise? Rise in sales, right? What's the run? Number of ads. Rise over run, what is that? Slope. Okay? So if I say it is strongly correlated, that means the slope is high. The rise per run is going to be high. So if I model this, the higher the slope, the tighter the slope, the better the return on investment as that particular value increases. If I have a very low slope or no slope whatsoever, what do you think would happen if I had an entirely horizontal slope, right?
No sales.
Here. Huh?
No sales?
Nothing. There's
Nothing.
no correlation between the input and the output.
Yes.
Okay? That would be that you're doing things, expecting something, and nothing is happening, right? You're pushing buttons and it's dead. It's nothing working, okay? So what we're doing here is we're pushing buttons, and we're attempting to see how we push different buttons at different quantities and where we put different values based upon these distributions. Now, where do these distributions come from? Where do all those little points come from? Well, imagine, huh? Surveys, okay, that's a prime example. So I actually would do marketing research, right? So part of, if I was an advertising agency, I might actually look and see maybe over the time that I have been working with data, or the time other companies that are willing to sell me their data about their experience, right? So data is a commodity. It can be exchanged, it can be traded. And it is valuable as a commodity. Why do we look at this and say that it has value? Previously, we may not have really been thinking about it. We might have been thinking about it in sort of this arbitrary sense that data has value. But now we recognize data has empirically accessible value, because the more of this information that I have, the more accurately I can determine what the efficacy of my expenditure, the cost, right? More ads cost more money, relevant to the amount of sales that I'm going to receive as a result. So if I have somebody selling me their hard-earned, they spent the money, right? In order to be able to determine how many sales they were going to get over that period of time. They took a wager, they took a risk of advertising at that certain rate to, in return on that certain number of sales over that period. They collected that value over that time, and now I can glean something that I can use to optimize my expenditure to income ratio. So when I say that there's a value to this data, absolutely. The value is efficiency. So the more efficient you are at this process, the better off you're going to get with regard to not spending as much on advertising and getting more sales. Now think about it this way. If we say that there is, to a certain degree, a correlation, let's say at the base here, we notice something about this little cone. Notice something about that little cone of information. There is something called the law of diminishing return. Anybody heard this? Okay, the law of diminishing return is actually more of a sales marketing kind of gimmick in a sense, because what we've noticed is that saturation, the more you see that ad on YouTube, right? There's always that one ad that shows up on your YouTube channel, like every video for like a week for some reason. Like, I don't know why, it's just they're paying a bunch of money, they want it in front of a bunch of eyeballs. But you get to the point where you're like, I literally would not buy this product if I wanted it, because you're sick of it, right? You've seen it so much, you're just done, okay? It can get in your brain, you're done, you're overwhelmed, all right? So what's actually happened here? Look at this. Sales are on this axis. So this indicates that there's a lower band of the curve where certain types of increases in quantity of ads that are being distributed are actually not creating that high value return. They're not creating more sales. We have some that are actually kind of, the quantity is getting less, right? The sales return is getting less for even an increase in quantity value of total ads that are being published. We also have other elements at the top edge that seem to be moving more quickly than the average, if you will. Perhaps they are well-crafted ads, maybe they have a broader distributional base, maybe they're just shorter and more effective, okay? There's a variety of things involving the psychology and construction thereof that we're not going to get into, but the idea being it is not a one-to-one return from relationships to what we see the output. Now look over at radio podcasts, right, and note that there are a few down here in the bottom that at small numbers, we're still getting some sales, all the way up to a decent amount of sales, to all the way over here where we have a lot of ads and almost no sales. So that's a huge diminishing return, right? The more ads, seemingly, the less sales. But we also have a big split at the top where we have a bunch of ads and a bunch of sales. So the consideration there is that we can't be fully sure about where we're going to land with anything. There is a randomness to these processes. However, we can make educated guesses. Well, those educated guesses are based upon likelihoods, outcomes, and probabilities. So if we look at each of these as a separate set of values, we can say that we're going to run a regression, that is an attempt to linearly relate via the rise over the run of the values within this space. Now, we say with each of these as a separate line that we're only able to understand a small aspect or a small part of our underlying process. The true underlying process is going to be a balanced optimization between all potential types of advertising. So what we're going to say here is that sales is in fact actually a function which takes in the quantity of ads put in all three modalities. So it's a three-dimensional function. Now, what does a three-dimensional function look like? Anybody want to give me an idea of that?
Well, if you were to stack those graphs, would that create three dimensions? Or is that not?
Well, let's first consider the fact that we don't necessarily want to project them all on the same incidental axis, right? So sales is still the ultimate, the divine, like, approach, like it's the desired outcome. But because of the fact that sales is actually, would be considered what? It's a fourth dimension. So this becomes a fourth dimensional graph. Because we have three input dimensions and one output dimension. We don't know what fourth dimensional graphs look like, right? Immediately that's a problem, because I can tell you what a three-dimensional graph looks like, that's a surface. But what ends up happening in fourth dimensions is what's called a hyperplane or hypersurface. Now, we can calculate it without even knowing how to graph it. But let's first look at the notational aspect of how we're going to do this from a computational perspective. We're going to acknowledge that we have some target or some response to our system of input. We're going to, the market responds, right? People respond to our advertisement. And Y will be that vector which we utilize for that purpose. Features or inputs to the model will follow the pattern of using X as the input. Now, X in this case is vectorized, meaning that it can contain multiple elements within it. In this particular case, X contains three elements, our original three items. Our YouTube, our podcasts, and our social media, right? We are going to then write the model as Y, the target, is equal to some function. This is the underlying relationship between the market quantity and our desired input based upon the sales, times that particular feature vector, right? So this is the f of x that we're going to look at. So this f has multiple elements, but we're also going to have this little thing over here to the side. What's that little eta? Error, okay? Now, why does error exist? We should say that we should be able to easily just do this. We don't need error. We just say f of x, y equals f of x. Everything we've done in all of our other algebra classes just says f of x. Well, I like to say that this error eta is a bit like C in calculus, all right? As a result of integration, we have a certain unknown characteristic that is quantitative based upon variance. That's just the noise in the universe. This can be the mechanism by which we acquire the information is noisy, mechanism by which we digitize the information is noisy, or there are unknown factors that are not computed within our model that are resulting in slight changes of the distributional characteristic. That is the ones that had high sales or high advertisement numbers and low sales, or the ones that had high sales and low advertisement numbers. Okay? There's an element there that does not correlate to the underlying model. Now, where's the model relative to this space? The model is the blue line, right? The data points are the red dots. So there are variances that exist for virtually every point on this graph. There is a relational difference between the actual blue line that is my model, my ideal relationship, rise over run of the underlying system, and the red dots that make up that space. So this error, the eta, is going to be summational based upon all the values that are collected in that space. So what is f of x good for? With it, we can predict likely new points, okay? We're going to extrapolate or interpolate. Interpolate means that we are going to pull in values that are within the domain of the space that we sampled. And extrapolate means that we're going to go past the domain of those values, right? The max or min of the sample data. Now, partially this would be related to things like temporal data. We tend to think about temporal data as being extrapolated. We want to go to extrapolar, right? So it's a poll where we collect a survey, right? You go to the polls and you vote. When I say extrapolate, I'm saying extrapolar, meaning outside of the confines of the polling, what data has been given. So So if I want to project something to the future, or I want to project something outside of the scope of what I've already understood, I extrapolate. So once we understand these components, we have a relationship between the system X such that X of 1 through X of P elements are informing which are the most relevant and irrelevant aspects of some system. Now the example given here is one that we'll discuss later on, in the effect that, let's say you're looking for salary, right, the total amount of money you're making as part of the job. You can have a variety of factors. Let's say seniority, right, how long you've been at the company. That often implies that you're getting some raises along the line. You have your years of education, and those have a relatively big impact on income overall. But marital status, right, whether you're single, married, or divorced, is not actually seen to have as high of a correlated impact on that system. So while we can collect that data, while we can collect something like marital status, there isn't always a correlation between all elements of X and all outputs Y, right? We're just saying that because it can be collected does not necessarily mean that it affects the system. And even if it does affect the system, it might affect it in such a minor or inconsistent way that adding it to our modeling does not enrich the process. There's also another problem that we're going to talk about there that is something we have to balance throughout the entirety of this course. This may seem a little primitive from an analytical perspective, but if you don't understand this stuff, it makes it harder to tie it to some of the concepts that we're going to look at later. The nice thing about this is if you get this, and once you truly get it and integrate it in your mind as a model of how models work, you will find that the rest of almost everything we do in the class tends to follow this same pattern. There is a pattern for the mechanism of creation of the model and the evaluation of the model that largely follows one overarching paradigm. So depending on the complexity of F, we may be able to understand how each component of X such that X of J elements of X affect Y. We're saying depending on how we go about the process, we can decompose to a certain degree the independent factors of X such that we can see the correlation or change of values for that particular element of the vector as it relates to the output Y. However, as models increase in complexity, this gets harder and harder because you have factors that weave them together, right? It all gets baked into the process and it gets difficult to work back to the individual factors from the overarching system complexity. Whenever we have something like a strict linearity, it makes it fairly easy for us to be able to understand. But whenever we have something that does not have a strict linearity characteristic, meaning that there is a change in the value of the slope as there is a change in the value of the predictor value, then we're going to be looking at a non-linear system. Now we'll look at non-linear a little bit later on, but what we are going to be asking here is something that I think will stick with us probably as long as we're going to be in the class is, does there exist an ideal F? Ideal meaning that there is not one that is better than this one, right? The answer is yes, but we'll never find it, all right? The reason why an ideal F exists is because in theory, I can explain to you how all relevant error can be minimized in the system. Matter of fact, if I had all the data, I can make a perfect model for anything. When am I ever going to have all the data? Never, okay? Partially because of the fact that the data is still being made right now and will continue to be made likely forever, okay? So instead of sort of looking at this from the standpoint of saying that we're going to ever fully understand it, this is just the best we can do under the circumstances given what material we have at play. So we're going to say that for any value of X in some system, let's say X selected at 4, there could be a variety of values Y that concur with a value X of 4. Note there's a band of values for X of 4 where samples have been taken that have related to the underlying system. So the data itself does not follow functional principles, right? Many times this can be confusing to people. That they tend to think about it from the perspective of saying, well, if there's one X, then there should be one Y. Yes, that's how functions work, but data does not work that way. You can have a variety of samples, a variety of times that you collected a sample with a value of X of 4 with varying different Y values. The argument can be, let's say we're thinking about color of a bird, and we're thinking about wingspan, right? You can have a variety of birds with 4-inch wingspan. They can have a whole different range of colors in that space. Or you can have a bird of a specific color with a variety of different wingspans. The notion is that individuals, which comprise the actual data points of the sample space, can have similarity with respect to some feature that they contain, but then differences in other aspects that change the relationship to the target value Y, right? The thing we're attempting to predict. Now, the function that we create from this does have to have a certain degree of convexity, right? It must have that relationship of having a single output for the single input. So the function that we're describing is actually constrained further than the underlying data system. That is part of what adds and creates the error in the system. Thus, we will only be able to accomplish or arrive at a specific subset value or expected value, which is the localized mean of the data as prescribed. So if I want to do a regression function here, what I'm actually describing is the expected value for Y, or the localized average. I take that little column along X, and I average those values out, and I end up with a singular point. That is actually what I'm describing when I talk about regression. But what I'm going to do is I'm going to change X by small incremental values throughout the entirety of the space, and at each region I'm going to prescribe an expected value. That is one methodology by which we can accomplish this process. It's one that's computationally expensive and intensive, and depending on the step size of X will depend on the granularity and quality of the value for the regression function, right? We also have to keep track of all the expected values or all the individual incidental values as we go through this curvature. By doing so, I will not describe this in a mathematical fashion that we're comfortable with. It won't be some sort of like parabolic x squared x cubed kind of configuration, but instead an array that describes this line as it transects the surface. As I said beforehand, it is the comprehensive methodology by which we would compute something like this relatively by hand. Now, most people don't recognize or understand that it is only within the last 100 to 150 years that we've stopped doing this stuff by hand, all right? Because even within the last 60 to 70 years, that many of these things have been viable in terms of being able to have any kind of machinery to compute them. So previously, this used to be the job of a computer, which was a person who sat at a desk all day, tabulating values in order to try to create these metrics. So things like firing solutions for artillery in the military had people that just sat at a desk all day looking at numbers and computing outputs. So we're going to define a regression system slightly different than the one we were looking at beforehand for a generalized format, such that F, which is going to take in these three vectors, will have some expected value for Y relative to each of those feature vectors. Now we're doing the thing we did beforehand with the averaging based upon a spatial correlation, but instead we're going to be doing it in 3 dimensions simultaneously. So we're essentially finding a point on a surface that is going to be the average of a cloud, right? Now we have a 3-dimensional cloud of data, and we're going to find the center of that cloud. And we're going to say that our line passes through the center of that cloud. The ideal or optimal predictor of Y with regard to this system is going to use something called a mean squared prediction error. Now, this is the first time we're going to be looking at this, and you will see this a lot, of this idea of square error. The first thing we do is we're going to say that G of X is related to our underlying prediction system for all G points as estimated as the expected value for that location, the localized mean. Okay, so as we're moving through that space, we're going to take the average of the space we're surrounded by, and we're going to say that we're going to try to favor everybody as equally as possible. Part of it is the idea of being sort of fair, but the idea also think about this from a spatial perspective. If I want to guarantee that I'm falling within the center of the space that is now constrained or defined by the data points that have been given, I will have the highest likelihood of falling within the appropriate range when I'm dead center, in the middle of everything. So by taking that middle point, taking that mean of the cloud of values, I'm increasing the likelihood that my prediction will be correct in future cases, or that it will be as close to correct as possible. Because if you think about it this way as well, if you have a circle, and you want to say that along the edge of the perimeter of the circle, you want to be able to draw a vector with the shortest distance from a single point placed inside of it. What is the location that has the shortest vector to all of the points around the outside of the circle? Just the center of that circle. So by going to the center, we minimize the possibility of error, right? That is a value falling outside of the space. Now, the values can technically fall anywhere within the recorded value or even outside the recorded values provided. But their likelihood of doing so decreases as they get further away from that center, right? This is intuitive. We recognize this to be the case. The likelihood of falling farther away from the mean of a sample is decreasing linearly in that fashion. So if we say we want to increase or optimize or maximize, which is the ideal of ideal or optimal likelihood, we do so by ensuring that in the future, our probability or likelihood is maximized. So in this case, the maximization happens by minimizing the error characteristic, right? So what is the error characteristic? It is the target, the desired element, minus what we guessed, right? The function g of x. So we take the square of that, right? Relative to some value of x. So we're going to input a value x. We're going to take that times some function g. We're going to subtract the value that we guessed, our guess function, from our desired target. And we're going to say that the error, the total error in the system, is a summation relative to the square of all of those errors. Now, what are we getting the square of? Why are we using the square? Because some errors are going to be negative and some errors are going to be positive, right? Some values are going to be over-desirable, some values are going to be under-desirable. So since we're subtracting them from the target, we're going to end up positive and negative. We want to know the magnitude of the error. So what we're going to do is we're going to square that vector such that we can sum them all up and we can tell the total amount of error we're making. Because we don't care whether that error is positive or negative, we just care whether there is error. We are going to utilize that assessment of the error to attempt to minimize this by adjustment of the parameters of the function g for all points x. We're going to then say that once a minimum error eta has been established for some y of f of x, that the error becomes irreducible once we can no longer make any useful adjustments to the underlying function. Meaning that we've gotten rid of all the error that we can adjust out based upon our model, and the remainder of the error is now based upon variance, just the randomness of the selection and sampling process. This idea will stick with us throughout the remainder of the course, and this notion of irreducibility in error is based upon a breakdown between these two things. Now we're going to replace the idea of the guess function g of x with another idea for notational perspective. And I'll cover this slide again in brief whenever we have our first class next week. But what I like to do is I like to try to get through this a little bit, get an introduction, and then back up and do a little bit, forward, backwards. But this notation matters here, right? So for any estimate f hat, right, of some underlying function f, what are we looking at here? F is the real truth. That is the ideal function. That is like the idea of a theoretical function, right? Think about theoretical mathematics, theoretical electronic circuits, theoretical physics, right? It doesn't really exist in the real world, it just exists on paper. So f of x, an ideal perfect f of x, exists on paper. That is the function which perfectly models the true underlying relationship between something, right? I drop an apple, gravity affects it. It is the true form of the real force that is acting upon that object. My version of an example of that particular system will actually be f hat. Now, maybe you've seen hat as a vector in physics. We're just going to use hat as a designator that this is the guess function. This is the best we can do with what we have. So once all relevant reducible errors happen, let's look at this. If y, right, we have y over here, we say the expected value, mean expected value of the error in the system is related to y here, I'm going to re-express y as f of x. Since the true y is caused by the true underlying functional form, then I will say f of x, the true underlying model, minus my best guess at the model, right, squared. This is going to be the aspect of the error that is reducible, because I can improve what? I can improve my guess. If I adjust the slope of the lines that I'm using as part of my regression, the total summation of error in the system will potentially be reduced. Once I have reduced all relevant error as a result of my guess function, the only thing that's going to be left over is error as a result of variance, all right, or variance within the system due to irreducible error metrics. We will continue on from here next week. Thank you guys for coming, and we may have like a slight little, maybe a little quiz thing on Monday, just for to see how everybody's tracking with what we're doing so far. So, thank you much.